Hello and welcome back. In the last video, we laid out the groundwork for how we could go about solving for the mass of the Milky Way galaxy using the Earth's and the Sun's orbital velocity around the center of the galaxy and our distance from the center of the galaxy. And I promised in this video we would actually solve for the mass of the galaxy. So I am a man of my word. Let's do it. Okay, lots of new space, new whiteboard. Let's actually do this. You might remember that our formula is mr equals r times v squared divided by g. And in this case, let me move this down a little bit so you can see it. There you go. And in this case, we happen to know what r and v squared are. R is our distance from the center of the galaxy. We've already written that number down in class on Tuesday. So R is 28,000 light years. Now, G is going to have units of meters and seconds and kilograms, so light year is not a good unit here. We're really going to need meters. So I happen to know that there are 9.5 or so times 10 to the 15 meters. Oops, I'm losing you, aren't I? Sorry. In 1 light year. And so I can multiply that by that, light years go away, and I'm left with meters. If I multiply 28,000 by 9.5 times 10 to the 15, I get a number that's like something like 2.65 times 10 to the 20 meters. That's a big number. A 1 with 20 zeros after, actually a 2 with 20 zeros after it, or a 2 with 20 digits after it. But you know, a meter is rather small and the galaxy is rather large, so it shouldn't be too surprising that that's where we are. Okay, we also need to know the sun's orbital velocity about the galaxy. That number is 220 kilometers per second. Again, we want meters here. There are 1,000 meters in a kilometer, so you just need to multiply this by 1,000. This is 220,000 meters per second. Easy. And if you remember, G is 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. Great. Now we can plug all this in and see how it goes. So we've got our MR over here. R is this number, 2.65 times 10 to the 20 meters. V squared, 220,000, quantity squared, divide by G, 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. Plug all that in, and I'll give you a chance. If you want to use your calculator, you can. It's probably a lot of fun to plug those numbers in, right? If you don't want to, you can take my word for it. This comes out to be about 1.92. Well, it's about 2. It's 1.9 or so, but let's call it 2 times 10 to the 41. Oops, and I wrote 14. I really meant to write 41. Sometimes I have writing dyslexia and the wrong number comes out, even though I want to write it that way. What are the units on this number? Well, I didn't write this. This is a meters cubed. I've got a meter squared and a meter on top, and I've got a meter cubed on the bottom. All those go away. I've got second squared on the top. This is actually meters per second. So this becomes meters squared per second squared. I've got a second squared on the bottom there. I've got a second squared on the bottom there. Those go away. I've got a kilogram in the denominator of the denominator. That moves up, and that gives me kilograms. Great. 2 times 10 to the 41 kilograms. Well, that's a large number. I mean, it's gigantic. I mean, truly gigantic. Let's write that number out. I'm not sure I can fit it on the whiteboard, but let's try. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41. That's how many kilograms of mass there are in the Milky Way galaxy. It's a ridiculous number. I'll pull some commas in there if you'd like. It doesn't really matter though. I mean, it matters. Look at that number. I'm sure it's got a name, but I don't know what it is. And honestly, kilogram is just like meters is the wrong unit to use for measuring masses of things in the galaxy. What is a more useful unit? Well, we really want to know how many stars there are in the Milky Way, right? So maybe if we know how many solar masses worth of material that is, that would be a more useful number. Well, you have to know how to do that. You need to know how many kilograms there are in a solar mass. I happen to know, because I'm an astronomer, that one solar mass is equal to 2 times 10 to the 30th kilograms. And those numbers work out rather nicely. 2 times 10 to the 41 divided by 2 times 10 to the 30th, the 2's cancel out. 10 to the 41 divided by 10 to the 30, all you have to do is subtract the exponents. 41 minus 30 is 11. M of R equals, you're almost seeing that. I'll raise this up a bit. M of R equals 10 to the 11 solar masses, which is also a really large number, but that's more like the number of stars in the galaxy, 100 billion. And that's how we know that there are about 100 billion stars in our galaxy, because that's how much stuff there is in the galaxy. When people like Carl Sagan says billions and billions of stars, we mean it. That's a big number. That's 100 billion right there. Okay, so that's pretty cool. We can, in fact, measure the mass of the Milky Way using nothing more than how fast we're orbiting the center of the galaxy and how far we are away from the center of the galaxy. Okay, let's go back to PowerPoint. Answered a lot. Okay, now let's think about rotation curves. If you remember back, there was a class in early February, and I said, remember this concept. This concept is going to come back and be important later in the semester. Well, today is that semester. And the concept at the time, we were talking about Kepler's laws, and we were talking about how fast objects in the solar system, the planets in particular, orbit the sun as a function of how far away they are from the sun's center. And that is what we call a rotation curve. And I even put up a rotation curve during that lecture on Kepler's laws so that we would have some reference at this point in the semester when we're going to be looking at other things. So if you remember what the rotation curve of the solar system looks like, here is Mercury and Earth and Mars, say, at varying distances from the sun. Mercury orbits at a particular velocity, Earth orbits slower, and Mars orbits slower yet. And if you look at the rotation curve of the Milky Way galaxy, it looks something like this. Again, what are rotation curves? We make a plot. We have the x-axis is radius from the center of that system, in this case, the solar system. And this is V orbital. I'll call it V or VC, the circular velocity, how fast you are going as you orbit the center of this particular thing. And this is what it looked like for the solar system. The further out you go, the farther out you go, the slower your orbital velocity, the slower your circular velocity. We call this a Keplerian rotation curve. Because it is one that follows Kepler's laws. That's what it looks like for the solar system. Great. So so this is can be a confusing concept. So I want to do a top hat question, even though we're not going to do top hat. I want to know, what would the rotation curve of a bicycle wheel look like, right? So here is the center of this bicycle wheel, and I want to measure the velocity of orbiting spoke material all the way out to the edge, right? So the center, r equals 0, is going to be here. That's r equals 0. As you move out, this is the edge, r equals the maximum, right? So what does it look like for rotation curve as you go from the inside outwards? Are they all the same, moving at the same velocity as this thing spins? Is this moving faster? Is this moving faster? What happens as this thing goes around? Okay. If you'd like to get out of bicycle wheel and try it yourself, you can. I encourage that kind of thing. If you don't have a bicycle wheel, you can use a Frisbee or a ball or really anything that's circular, and go ahead and do the experiment, see what you get, and then we'll come back and talk about it. Okay, you're back. Great. So what did you answer? This is the Keplerian rotation curve, but this is not what this bicycle rotation is going to look like. So let's imagine, again, an imaginary particle attached to this point on the spoke and this point on the spoke, and imagine which is going to be moving faster, right? This is called solid body rotation because all of these spoke points have to make one complete revolution in exactly the same time, right? You can't have this spoke rotating at a different rate than this spoke because they all need to stay together, right? You can't have these things stretching out. And so it takes this spoke exactly the same amount of time to go all the way around once as this spoke point over here. Which of them has a farther distance to travel in that same amount of time? This one out here. The further out you are, the further path you have to travel to make it all the way around once. And you're doing it in exactly the same amount of time. And since velocity is distance divided by time, the time is the same for all of them, but the distance that you have to travel to make one complete loop goes up as you go out. And therefore the velocity has to go up as you go out. Here is what that looks like. The point at the very center isn't moving at all. It's just slowly spinning around at the center. As you move out a little bit, that point is moving a tiny little bit. As you move further and further away from the center, those spoke pieces have to be moving faster and faster to make that full loop in one cycle. And so the answer is D. That is what any solid body rotation curve will look like. This is what a solid body looks like. This is what the solar system looks like. Again, the solar system is not confined to rotating as a solid body. It does not. Mercury orbits in a much slower, much faster rate and in a much shorter time than, say, Venus does, and Venus the same for Earth. Great. So here's the question. Does the rotation curve, we're using the fancy RC here, look the same for the galaxy, look the same as the solar system? And the answer is no, it does not. And this is a very interesting fact, and it provides us with more information about the mass contained within the galaxy itself. When you look at the rotation curve of the galaxy, the galactic rotation curve, it is mostly flat. What do we mean by that? I mean that the velocity at which stars orbit the center of the galaxy is about the same no matter how far they are from the center of the galaxy. That's true once you get out away from the very center of the galaxy to a fairly high order. What does that look like? Well, let's go and draw it on our blackboard so you can see it. There we go. We had the Keplerian rotation curve. I'm going to draw another rotation curve right underneath it. That looks like this. And the rotation curve of the galaxy the velocity doesn't change as you move out. So aside from some weirdness in the beginning, it looks fairly flat. Doesn't change much at all as you go out. That's what a flat rotation curve looks like. Great. Looks flat. Okay. I think I'm going to stop this video there, and we'll do this something strange happens, because there's cool things about to happen. Something strange is going to happen once we get outside the edge of the Milky Way. Before we do that, I just want to point out why this is. Why is the galactic rotation curve different than the solar system rotation curve? What is different about the galaxy? Because the Keplerian is a very useful one, right? That is basically any time, that's what the orbital speeds of objects in the solar system, that's what orbital satellites around the Earth do. Keplerian shows up in a lot of different ways. What is different about the galaxy that causes it to not have a Keplerian rotation curve? The answer is, what is different about the galaxy than the Milky Way, than the solar system? Which is, in the solar system, almost all of the mass is at the very center and contained in the sun. As you move outwards, you're not encountering any more mass. In fact, if we go back and look at the, let me bring back the whiteboard. Here's the whiteboard. We've got some real estate on it now. If we bring back the whiteboard and think about this particular equation, m of r equals r times v squared over g. What does it mean that, well, let's think about this for the Keplerian case, right? All the mass is at the center of the solar system. And so as you increase r, v has to go down because m isn't changing. Increase r, v has to go down to save this from being an equal, to save this being equal. If m isn't changing and r goes up, v has to go down. What does it mean that as r goes up, v doesn't change? It must mean that m is going up. And that's exactly what's happening in the galaxy. As you, here's a view of the galaxy does not have all the mass at the center, unlike the solar system. The galaxy is much more smoothly distributed in mass. And so as you move outward in the galaxy, the m, the mass, is going up. So remember, m of r is only the mass that's interior to that orbit. And as you increase the orbital size, you are enclosing more mass, and therefore this number goes up as you go out. And it must go up at the same rate that r is going up in order to have v be the same. So that's what it means to have a flat rotation curve. It means that the mass that you're encountering increases linearly as you move outwards. If you double the radius, you have double the amount of mass inside that volume. Okay, we'll talk about the implications of this and other weirdnesses in the next video. Stay tuned.